Hi, folks. Welcome back. So, this is another episode of the Emergence Technical Chats podcast. My name is Vivek Haldar. I'll be your host, and let's go around and do a quick round of introductions. Prasenjit, do you want to start?
Sure. I'm Prasenjit Dey. I head the research at Emergence AI, and also I'm part of the Emergence India Lab.
So I'm Siddhartha Gadgil. I'm a mathematician at Indian Institute of Science, but for the last decade or so have been in automated theorem proving and hence now part of this Emergence AI lab on the side of formal verification, AI and related things.
Fantastic. So, folks, the topic we want to chat about today is something that is somewhat nascent in AI and in agents, but is going to be super important going forward. And that is, how do you bring this notion of formal verification to AI agents? And that is something that both Siddharth and Prasenjit and the team at Emergence have been looking at for some time. Um, so maybe we should start with just one very interesting announcement that Emergence made recently. You recently formed the Emergence India Labs, and specifically, you want to focus that on formal verification. So let's start there. Let's start with that announcement. What is it? What do you want the focus to be? And what was the motivation behind it?
Sure, I can go and then Siddharth can also add his color to it. So the whole point, right, of starting something as Emergence India Lab with specific focus on verification with a very particular focus on formal verification, right, is primarily for a couple of reasons, right? The first is that Emergence AI has been working in mission critical verticals where, for example, in semiconductors, drug discovery, airline operations, and so on, where any mistake, right, can cost someone tens or hundreds of millions of dollars, right? And hence, when an agentic system is used in those domains, one has to be very careful and one has to have some kind of guarantees, right, of what kind of a consequence that action could result in, right, from a system. And hence, it's almost like some of these are kind of single door situations where once you have done it, it's done, right? You cannot reverse back those decisions. So hence, we started collaborating with Professor Siddhartha Gadgil at Indian Institute of Science, and where he was also very interested in how do we make AI more predictable, more verifiable, more certifiable, right? And that's where this whole idea of Emergence India Labs, specifically focusing on autonomy, in which verification is a very important part of the pieces of how we achieve autonomy, is where this whole idea came about. But Siddharth, your thoughts too.
Yeah, so I should add to that. So of course, for safety critical systems, people have been trying to use formal methods for a while. They become easier with AI because AI helps you formalize it. But it's not just in safety critical systems. For example, formalization has been used for mathematics theorems. I mean, nobody's life really depends on that. But the point about AI is also it's producing so much volume. And that will just sort of flood the whole system if you did not have a decent way to filter. So simply to cope with the enormous ability of to generate stuff with AI, and good fraction of which now a large fraction of it is good, but some persistent small fraction of which is continues to be dubious. You pretty much have to try to use formal verification anywhere. I mean, even if it's not something which is that crucial. Otherwise, you are flooded with this volumes of output. You don't really know what to do with it, and you can't just simply accept it as it is. That would not work anyway.
Yeah, that makes a lot of sense. And especially now that we have agents being more autonomous, running for longer and longer periods of time on more and more complex tasks on their own, it becomes very important to get some assurances about their final output, which is kind of what you're trying to put some bounds on or some proofs around. So let's talk a little bit about how these two fields are beginning to meet. So formal verification, of course, has a very long history in both math and computer science. Some of the earliest pioneers in computer science really wanted to focus on formally proving their programs correct, and that has a rich history. Agents, of course, a very new thing, but like we were just talking about, they're becoming more and more autonomous. So, can you talk a little bit about the current ways that agents try to stay on the rails? They do some kind of testing, they do some kind of verification and feedback loops, and that has gotten us this far. And it seems to be working in some scenarios, not so well in other scenarios. So, can you talk a little bit more about why the current ways of getting assurances from agents, the kind of typical verification reflection loops we have, why are those not sufficient? Where do they break down? And then how can formal verification help improve that?
Yeah, so, well, one thing I can say, so for these things, even if our goal is real world industrial things, mathematics is a great lab. So there is this fantastic agentic system called Aletheia of Google DeepMind, and it has done very non-trivial mathematics. I mean, on par with good mathematicians, certainly, not yet truly breakthrough results. So they did really an experiment. So it is a self-verification in the agentic style, with an agent criticizing another, with detailed skills and prompts which tell you what are the things you should look out for, and so on. So they did many things, but one of the things is there is this collection of problems. They thought they'll do a systematic experiment on that collection of problems. These Adash problems, as they're called, posed by these. And they found that, yes, it solved a good number of them, but it gave wrong proofs in spite of its agentic verification in a good number of the cases. And a person had to check and rule that out. So we have a test, I'm saying an actual quantitative test, that agentic verification is leaky. It hits a lot better than the LLM's first output. But this, fortunately, we have not tested in the wild, maybe where the consequences would be much worse. But this becomes a great sort of safe lab to check, was tried. And so, in fact, in mathematics, again, formal verification is more or less routinely used if somebody claims they have found a new proof with even LLM assistance. I mean, it need not be fully, whether it's fully autonomous or interactive or whatever else, it's all becomes sort of routine to, it's usually the lean prover in which things are formalized. So, yeah, it's been tried. And one case where you could nicely measure things, it's been found that it's great. It brings down the error rate a lot, but it still leaks quite a bit.
And just to add to that's point, if you look at it fundamentally, right, the whole notion of agentic verification is literally that you have the generative part of the system, which is stochastic, right? And you're trying to use another stochastic system to verify the work of another stochastic system that generated the output, right? Which kind of is a recipe for disaster because you don't know which one is the right one, whether the verification is hallucinating or the generator is hallucinating. So here, even though we can heavily, people have looked at multiple agents with different personas to kind of look at different aspects of a result, which is called the committee of agents, or people have looked at LLM as a judge, right? The most basic thing, right? Or heavily prompting or fine tuning the LLM to say, okay, here is what, your guardrails are. Here are the set of things you focus on, right? But then once it is in the network, you can never know what exactly it's finally going to do because, the network itself is so complex that all you can expect is that, yeah, I have done my best, right? It's my best effort of what I had to do for tuning this particular LLM. But after that, it's kind of best effort, right? You have no guarantees that you can provide. Whereas when you go into formal verification, you can precisely one define the constraints, right? Define the properties you want to satisfy and provide guarantees to say, okay, given these properties, I am able to say with mathematical rigor that these properties are satisfied, which is outside the model. The important thing is that this is outside the model and you have full control over that particular verification scaffolding.
Yeah, that's a great point. So, yes, the self-reflection critique loops are very common in today's agentic systems. but they themselves depend on non-deterministic models, whereas now you're bringing in a deterministic, provable infrastructure that does automated theorem proving and so on, to give you proper guarantees that some properties will be satisfied. So let's back up for a bit. We've been talking about automated theorem proving, but just for, those who are not totally familiar with it, maybe can you give a very short 1 minute overview of kind of the current state of the art in automated theorem proving, how it works, what the kind of well-known systems are. People might have heard of Lean, but might not know how it works internally. So just at a high level, can you give a brief overview of how that infrastructure works?
Yeah, so there are actually multiple dimensions to this. There is what is called automated theorem proving, and there is like Lean, which is interactive theorem proving. And automated theorem proving's been around for a while, and it's something where you have a bunch of logical deduction engines, you'd say. It goes back to Boole and with propositional logic and so on, that you can really calculate logic. So these are very powerful calculators. They can deduce things. They succeed or they fail. And Lean kind of started historically because Leo de Moura, who had made Z3, which was one of these very powerful automated theorem provers. These are called SMT solvers. They combine a whole lot of methods. Found his users were frustrated because things almost succeeded and they didn't fully succeed. So you'd want to say like the user fill in the details. So now interactive theorems provers have also been around for a while, all the way from Automath in 68 and Koch and so on in the 70s, Mizar from long ago. But they have Lean is the latest and has many advantages. So these are where a human and automation interact, and together we try to state and prove results. And ideally, automation will do most of the work, but humans can supply ideas, they can decompose things, they can even fill in details. Lean itself is the first case, maybe, of there is also Idris, one of the rare cases where it's actually a programming language. And you can think that in the programming languages, you have sort of stricter and more liberal ones. I mean, things like Python, you can write something and you have to run it before you find an error, unless it's really a silly one. A stricter one like Java, and then you go on to Haskell or Scala. They have type systems which will reject things more and more. And in Haskell, people like to say in Haskell that if it then it will probably run. But then it'll only run. It doesn't necessarily give you the correct answer. Now in Lean, you can specify things so much with there's an idea from the 50s, Curry-Howard isomorphism, and then further work that told you can specify the types as they are called so strictly they include just an arbitrary mathematical statement. So you can make it so that if it compiles, not only will it run, it will run correctly. And just to say personal experience, the way I taught myself Lean when Lean 4 came along was that I wrote a SAT solver in Lean, a basic one, what is called DPLL, which is a basic algorithm for it. There are many refinements in the new ones. It took me 1 month to write it. It was complex code. And the first time I ran it, it ran correctly. Now, I think it's almost astonishing that you spend 1 month on a program and it's utterly bug free. But that's because the compiler actually guaranteed it was bug free. I mean, that is the nature of it. It's a programming language, it works that way. It's also a theorem proving system, and I should say, just as important as the language is the fact that somehow mathematicians got hooked to this. Many good reasons it happened, but also just chance natures, and a very large library of mathematics has been built in Lean. And so when you prove things, you don't have to start from scratch. You start from an already existing rather large body of results with respect to which you can prove this.
Yeah, thanks for that overview. So building on that a little bit and, trying to join these fields, agents and formal verification. So just to make this a bit clearer for our audience, can you maybe take an example that would be common in enterprise situations that people are currently building agents for or trying to build agents for, and then add in this layer of how would formal verification help such an agentic workflow? I know the folks at Emergence have written some blog posts about this, and we'll leave links to all that in the description. But yeah, help walk us through a concrete example and how it helps to bring in formal verification.
Yeah, so one example which we're actually working on is if airlines schedules. So airlines have schedules and things go, when they make the schedule once and for all, they're willing to throw in a lot of resources. But then you have technical issues with an aircraft, or you have fog or whatever disruption, and they have to quickly adjust the schedule. And this is intensive and not optimized, and agents are very good at optimizing it. Except that there are hard regulations here. And those hard regulations tell you, for example, a pilot is only allowed to fly a certain amount of time. Certain airports don't let you land after 11:30 p.m. and various other things. And you want to be sure that your agent has not violated any of these. And actually, an AI might do something silly. So you even have to, if you're planning an aircraft, you even have to make sure that it takes off from the same airport that it lands. I mean, of course, the plane will do that, but your schedule may not do that. I mean, so ranging from these kind of silly things to the serious things, you would want to have a check that thing satisfies. You want to do a little better than this, because the nice thing about a flexible proving system is that, well, we know that in an airport like Bangalore, you always have a lot of delay in taxiing because they're overcrowded. So you say a plane is going to fly, it's going to fly to Bangalore, and then it's going to go on to Frankfurt. And Frankfurt, you're not allowed to land after at midnight. So is it that if you have an extra delay in Bangalore, will you land after midnight? So you want to throw in these scenarios. The thing about an automated theorem prover is that you can lay out these scenarios and check if you're fine anyway or not. And there's no danger of a programming error. I mean, you could do these with conventional programming, but there what happens is that the nice thing about a proving system is you're separating your equations from the act of actually calculating or proving. So it becomes really easy for a person to see what's going on. And you have a person who has to make a decision. Okay, before I go in with the schedule, I'm worried about X, Y, Z happening in addition. And I don't want to create a mess if X, Y, Z happens, because there's a chance. And you have proved it's fine. Can you prove that in spite of X, Y, Z, it's fine? And you can go ahead and ask for that. And maybe it'll fail to prove it, but that's part of the point, because the failure will tell you what can go wrong, and maybe you should adapt from that.
All right, so that's a great example. And I know in situations like that, people will want to bring in agents, but they'll want the agents to have the kind of provable properties you mentioned. So let's dig in a bit deeper. So if you look at the architecture, and you have an agent that's driven by a model and some kind of harness or some kind of scaffold, and you also have an automated verification system. Let's assume it's lean or some theorem prover. So how are these two interacting? Where is the proof generation and checking happening, and how is that interacting with kind of the output of the agents and the agentic loop? So talk a little bit about that.
Yeah, so the way we look at this is one is the hierarchy, right, of these different verification requirements you may have. But let's start with defining the system in a very simple way, right? There's the input, there's the processing, and there's the output, right? There are things you may want to already ensure, right, that it doesn't even get to the input, right? That, yeah, there are set of values, there are things that are getting into the system. You may want to literally check them and throw them out at the input level. So imagine you have a agentic system, right? And it's getting some set of inputs, it's processing it, and it's giving you an output. Before it even enters that system, we could have, so we have what we call a verification control plane, right? Which literally does this orchestration of taking the output, taking any of these values that are going into the agentic system and saying, okay, here are the inputs. What do I need to, given that, for example, let's take the airline operation that Siddharth talked about. These are the values that are going into the system, and you could perform simple checks like, okay, is the schedule that's going in satisfies the plane airport that it landed in, it's taking off from there, right? You could run those kind of even simple input checks, which means that the verification control plane takes this and passes it on to the formal verification engine and says, okay, here, according to the rules that I have, the constraints or properties that I have, does it fit there? So right at the input, you can throw away some things, right? That, or stop it right there, even before it goes and processes, because processing is an expensive job, right? Because you're using the tokens of an LLM, right? So that's the first layer of check. The second is at the processing level, you literally have these agents running, producing intermediate outputs, doing this, as you said, right? The reflection loops, right? So there's a lot of churn that happens, right? And here again, right, every time a particular intermediate decision is taken or this agent is doing some kind of processing, you can literally check that the program that it is running, right, because it generates a lot of code right in between. Does this even satisfy the kind of constraints that we are talking about? Or the right at the reflection stage, right, did it even the output that it produced to reflect, I can stop it right there. So literally you can have at the processing layer stop things or even in some sense tier things based on the some of these feedback, right? Or I would say feedback signals that you get from the formal verification system. And the third is the output itself, right? I got an output. Should I take that? Is this something that I should take already? I could take an action on. That's critical because now here for some of the safety critical systems, the output of or the action that you have given out in saying that I should go and take that particular action, that can result in a big consequence and cost. So hence the output should be even more thoroughly checked, right? Through these kind of, so here in case, if you look at it, formal verification is really the gold standard of that. Here is something that has been certified as true globally. You need to perhaps run that and check the output before you even send it to further downstream for any action to be performed.
Yeah, let me just add very briefly to that. So we are, I think Prasenjit already outlined. I want to say that when we talk about verification of agentic loops, earlier we were talking about verification of outputs, and even now we did. But there's also the verification of the behavior of agents, because agents have to have access to your API keys because they're going to be querying GPT or whoever else, Claude. On the other hand, for your convenience, they also have to be able to put things on a web page publicly, maybe send things by WhatsApp to a group, but they shouldn't be sending your API key by WhatsApp to a group. And so you don't want these kinds of things to happen. And so the behavior of the agents, in addition to checking their output, is something that we would very much like, I mean, we need to restrict, I mean, to prove that through all kinds of safety properties of it. There's a whole bunch of things that can go wrong in various ways, from an agent just grabbing all the resources because it's told to do this task really fast, but it does it by creating a huge key value cache and nobody else has any disk space left. Various kinds of ways, from grabbing resources to leaking keys. These are things you want to prove. It is, on the other hand, these things are really new. So how are we going to do it? Because we are not proving Python programs. What has been done in AWS, Amazon Web Services, in a similar situation with something called CEDAR, an authentication system, is to have a model in Lean, and you prove everything is correct in the model in Lean. And then you show that the production code is in another language, Rust, and you show these two are equivalent. But then actually the lean code also runs fast. So ideally, maybe we would want to push lean itself to production code, say it's actually a better language than Python or something, or some mixture of the two. So it's a challenge. We have to still understand it, but it's well worth doing it. I mean, it's well worth trying to make sure that if we have open clause should be open only in the good sense of open source, but not open in the sense of leaking like a sieve.
Yeah, that's a great point. So this is super fascinating. It's reminding me of some of the things I was studying back in grad school. So, when we apply formal proofs to a system, you can bucket the properties into these two large categories. One is safety properties, and another is liveness properties. And very roughly speaking, safety is focused on proving that bad things don't happen, whereas liveness is focused on proving that good things happen. That's a gross simplification, but so liveness focuses on things like that you're actually making progress, because you could trivially have a safe system that just doesn't do anything. So we've spoken a little bit in this conversation about safety, and some of the examples you gave were very focused on safety. I'm curious to get your thoughts on, do you think formal verification can also help with liveness properties for agents?
Yes, I would say there are a couple of ways. But I'd say the most obvious way is in the sort of double negative, that you do not have to be excessively defensive. Because currently, when you think about systems like OpenClaw, I mean, I won't do it myself. I'm scared of what it'll do, whether it'll delete all my files. I mean, when we are using agentic systems, we are kind of worried. So we are stopping the permissions. And so if you're going to be safety conscious, even moderately, that you would be in sort of ordinary life, then to ensure safety, you may have to be extremely defensive. And the mathematical guarantee of safety will let you just give permissions much more freely. I mean, you'll stop having to watch your back so much. You'll stop having to have many layers of redundancy. You'll just say, I know I'm safe. Let me go ahead. And when you have liveness, I mean, you can try to make things live in this sense. Yeah. So a close analogy. So these things are so new that this cannot be has not been tested in production, because there hasn't been a system where I suppose there is liveness with I mean, safety with formal guarantees versus, as I'd say, very defensive kind of safety. But there are closely analogous things where we do have experience. Like again, AWS has been a pioneer in formal methods across many areas, and in Amazon Web Services, they found that they can optimize much more aggressively, and this liveness is kind of the similar nature, and push code to production much more quickly, because they don't have to be so scared about something having breaking, because they proved that nothing is going to break. So that's a sort of double negative, that when you're fearing things, you may want to be bold, but that's rash. But a guarantee will mean that you stop fearing, so you do as much as you can, allowing guarantee. The other dimension that I can see is, of course, is actually proving liveness. That is to say, when you want to prove something is, at a simple case, you have an optimization problem and you break it up into sub-problems. You want to prove that you're close to an optimum, rather than just that you satisfy the constraints that you want to do. This, I have to say, is, I mean, maybe I'd say that's why we should have a lab, because this is kind of, it's hard. One has to think about it. One can hope. I mean, it's not sort of proving liveness would be a great thing to do. I see immediately how to do it, how widely applicable it would be. One hopes so. What one can say is that we can avoid excess defensiveness, and hence hope for liveness. We'd love to prove liveness too.
Yeah, and just to add a little more color to this, right? And Vivek, you touched on a very interesting and important topic, right? That we talk about almost every day, right? Is that these advent of these kind of multi-agent systems, right? And OpenClaw has shown possibilities both in positive and negative directions, right? These multi-agent systems are exactly trying to, if you really want to build a good multi-agent system, you're precisely trying to balance that, right? Because these agents can go in a completely different direction, cause safety issues, but then you really want, and this is what we all hope, that these multi-agent systems, when they interact, these agents interact, they result in some kind of emergent behavior. And we are really looking at that kind of possibility of emergent behavior. That's an aha moment for us to say, oh, wow, I didn't even tell it to do it, right? And it did it, right? So that's where I think your point about liveness is very important, because the liveness ensures that you could observe this kind of positively reinforcing emergent behavior. Now, the thing is that when you have these possibilities of emergent behavior, you also have you have these agents which are also self-improving, because now when the system is no longer at that state where it started from, where you had tested it to be correct. So here you have a further challenge, and which is why, as that said, we need to understand, right, how exactly to formally verify systems that are self-improving, that are evolving, because some of those, there may be global constraints of things like that things are not being leaked and so on. But are there other things that you may need to ensure, because they have completely moved away from where you started from, because these are evolving systems. So I think this area of multi-agent systems and self-improving systems with emergent behaviors is a very interesting area for us to say that how do I formally provide formal guarantees and formally verify these kind of systems.
That's fantastic. Yeah, that is such a sorely missing thing in the agents of today. That you made a great point, which is that you can go much faster and be much bolder if you have these guarantees, right? And I'm guessing perhaps it even leads to a lot of performance and efficiency because you might not waste so many tokens going down bad paths or irrelevant paths, right? So the potential for not just correctness but also efficiency is pretty interesting. So that kind of brings us full circle. So coming back to the formation of Emergence India Labs, what are the first few highest priority problems you're looking at specifically?
Yeah, I could take a shot and then Siddhartha, right, please chime in. So we have been working on some of these problems which are in these kind of mission critical domains, for example, semiconductor manufacturing, drug discovery, and as Siddharth said, things like math as an area, what we call the AI for math, and also airline operations, which are also safety critical. So we are already, in some sense, we have been deep in this domain already. And we believe that these are very good play areas, right, in which we can start to now see, okay, what does formal verification mean in each of these different domains, but also how do you even model that the formalism, because it's not clear that in each of these domains, because after all, the system is as good as how well you specify it. So if specification, right, and formalization is the bigger problem, you have this issue of how do we formalize that domain, which is where the whole area of auto-formalization comes in, because you cannot have human starting to specify every detail, right, of everything in a formal domain like lean, and you could probably have ways by which natural language specifications can be converted into formal specification. But it's a very active research area which Professor Siddharth has been working on himself, right? So in some sense, I would say the whole formalization and specification itself is a big focus for us, which what we call as trying to specify that particular domain. Because once you have that, then comes the step of proving, right, theorems in that domain to make them highly predictable and certifiable.
Yeah. So maybe the way I view this is that we want to sort of take formal specifications of systems, both broader and deeper. So by broader, I mean just going broader would mean there are plenty of domains, like as I said, with the airlines operations, where it's really just a matter of execution. It's not difficult to write down those constraints. It's not difficult to set up the proofs. It's a matter of doing it. But also it means that because the domain is simple enough, it can be specified in its own language or with a JSON schema or whatever else. So there are cases where the technology is there. It's a matter of doing it. We have to expand to more and more such domains. And so these are domains where we're looking at fully specified properties and where the specification is small enough that and you can just expect an airline to an LLM to communicate the specification straight to lean. So that's as we go broader. But we want to go beyond this set of domains. So we will, of course, keep spreading. So first thing is, like as Prasenjit said, many things are not closed systems. You don't have a ground truth in advance, and you want to have reliability without necessarily having a property that will check the answer for you. So this is one of the challenges. Can you generate things to prove as well? Second challenge is if your domain is complex enough, then again, as Prasenjit said, you can't depend on saying that we have a small language, a schema that the thing will have to do. We'll have to move to what's called auto-formalization, which is completely general translation from natural language to your domain sufficiently customized, because your generic auto-formalization system translates to mathematics, but we want mathematics plus the enterprise logic as well. So we will want to have that, the prompting various. So it's an issue of how that is done. And so yeah, so we will have to add in various ways. We want to extend to things which are not closed systems. We want to extend to things which are not. We will need auto-formalization. And as we've discussed already, we want to extend to modeling agentic behavior, not just output. So the goal is that successively we will be at the same time having a capability of modeling more and more. We will have actually modeled more and more systems and build the bridges, and at the same time have our core capabilities growing so that the ability grows to model more and more systems. And all of these things like auto formalization and so on are not just hit or miss. I mean, you just get better and better at it. And so you can handle more and more complex systems. I mean, there's systems which need none at all, systems which need it to work, but working, it already works fairly well, in fact, very well, but not perfectly. So relatively, so you handle more and more complex systems, more and more aspects of it, and systems with complications like external data and so and so. And I'd say the other goal of this kind of thing is not just in the system, but in the people you have the capability residing, because the case point, as I said, is some things are a matter of just execution, but this is a somewhat specialized skill to model something in a formal proof system, in our case lean, and do it. So we also want more people to have that specialized skill. So where it comes to just a matter of execution, there are more and more people who will just do the execution. So it's a skills of people as well as skills of the technology.
Yeah, just to emphasize that point, right, Professor Gadgil made, is that one of the key stream we have is because formal verification and lean, right, as a skill set, as a knowledge, is not widely available in especially everywhere, but in India in particular. And one of the initiative we have is to organize this kind of hackathons, summer schools, and so on, to be able to train people to build the capacity for people to be trained in formal methods as well as be experts in lean. So that's another piece of our whole mission. The other is we are going to work very closely with the open source community, because we believe that none of these we can do alone. It's a huge field. It's a, as we go deeper, we are going to build on things that people have done, or we ourselves are contributing to the community on which others can build. And that's how this whole field will get solved, or will make advances in this field. So open source contribution and community capacity building, right, is also a big part of our mission at Emergence India Lab.
Fantastic. So, yeah, totally love the stress on open source and engaging with the community. That's awesome. And yeah, I really do think this might very well be the missing ingredient that really makes agents go, so to speak. So that's a great point to wrap up on. But before we go, where can folks follow this work? Do you have, speaking of hackathons, do you have any exciting events you want to let people know about? What's coming up and how can people follow along?
Yeah, so we have a hackathon that we are running in collaboration with Indian Institute of Science in Bangalore. It's on 17th and 18th of April. We have been putting a lot of messaging on the social media. To follow us on Emergence handle, we'll continue to push updates. So we just closed the registration. We are going to now let people know. But the format of this is that we have 2 days, of which the first day is actually lean training. The second day is about projects that people will work on for the hackathon. And then we continue in an online format for about 10, 12 days, where all of these activities and the collaborations, there'll be tutors and so on. All of this is going to happen on the Zulip community. So we have set up an Emergence Zulip community server where all of these people can consult with the tutors. And finally, on the 5th of May, we are going to declare a winner and give out the prizes. The prizes are pretty grand. So just go to our webpage and go to the Emergence India Lab page, and you will see all the details of the hackathon.
Fantastic. That is super exciting, and we will leave links to all of that below. Thank you both for such a stimulating discussion. And all the best with the newly formed Emergence India Labs and with the upcoming hackathon. And thanks to everyone that tuned in. And we will see you next time. Thank you very much.